Okay, next slide, we will hear some more details, status of R&D. The next speaker is Murat Torlak from National Science Foundation. So he is serving as a program director on next generation wireless research. So let's welcome Murat Torlak.
I would like to get everyone attending this exciting event. I am Murat Torlak, working as a program director at Division of Computer Networking Systems at United States National Science Foundation. I'm on leave from University of Texas at Dallas, where I am also a professor of electrical and computer engineering. Thanks a lot for giving me an opportunity to talk at the 6G Global 2021 event. I will provide a little bit of vision from the vantage point of National Science Foundation, where I'm privileged to work at currently. I want to give a little overview about GE's different generation of cellular wireless communication standards. Obviously, this is not new to many folks attending this event. Sometimes the context helps when you want to look at the future. Brief look at the past, useful to see where we are heading. Many of you know how the mobile telephony first appeared. Almost every region had a different standard of mobile telephony. First generation systems were analog and supported voice communication, mostly using frequency modulation with little or no data support. Many of you also know that the GSM started off with a new, whole new mobile telephone system. GSM was a truly 2G system. Our transition to 3G had taken a couple of steps. For example, in case of GSM, there were GSM-based versions like Edge and GPRS, which were sometimes called 2G, 2.5G, or 2.75G. With these, we went from voice-only system to systems that also supported packet data. The packet data had become the primary driver. The email was a killer app, and the BlackBerry was a must-have phone. Then came 3G. 3G did not fully realize this vision at all. However, something very interesting happened with 3G. We got used to the fact that you could do things while on the move, and that expectations start building up, then create an ecosystem of other devices like Palm Pilots and the early generation of smartphones, coupled with touchscreen. Then came the iPhone in 2007. Of course, people were working on 4G, and LTE became a breakthrough technology. And today, that's where we are today. Today, we are developing 5G networks. There's a big question: what the killer app of 5G or 6G or any NextG system? I tend to agree with the people saying that there's no killer app and we are rushing into 5G without a killer application. But that doesn't mean we shouldn't be looking at what 5G is and what we have to explore. Yet we are already starting to talk about the next thing. Some people call it 6G. At NSF, we like to call it next generation wireless systems. It's something to remember though, by the time that 4G came around, we all got to reap the benefits of high-speed wireless. But my colleagues at NSF, and I think that the 5G is getting us used to the fact that every wireless user is expecting to have reliable data connectivity in any part of the world, wherever you want. And I think that's what 5G is going to get us. This is my 27th year in wireless research and my second year at the National Science Foundation. At NSF, I was privileged to witness the outcomes of some phenomenal work that NSF has funded over the years and continue to fund. The enabling technologies such as spectrum sharing, the use of millimeter wave spectrum for data transmission, massive MIMO technologies, and software-defined radios and software-defined networks. Of course, there's the much older history of helping to build out the internet, transitioning from whatever DARPA led initially to very specialized networks and networks that anyone can use. The internet is giving us 10 gigabits plus speeds with the help of optical communications. NSF has funded many foundation technologies that benefited many telecoms and internet-based companies such as Qualcomm and Google. Today, we are continuing along the path, and every year we fund on average 100 million worth of research on just advanced wireless alone. This number has been increasing steadily for the last few years. We have our core fundamental research program. We also have cross programs that bring all these different disciplines together to fund the work across multidisciplinary challenges. For example, we support interdisciplinary research teams that would combine the expertise of research in hardware, networking, and theory. We are not just looking at pure theoretical academic research. We are also forming partnerships with other US agencies such as DARPA, also companies such as Intel and VMware. We were looking at entire research space, mobile to edge, and to the core network, not just one-on-one partnerships. We also engage in multi-sector partnerships. Many of you may have heard the recent announcements around the resilient and intelligent next generation systems, the RINGS program, which is a partnership with about 9 companies and 2 agencies. The interest of the RINGS program from the research community was phenomenal. We are now reviewing proposals submitted to this program. Beyond that, there's the testing side. We believe that you need to have a robust testing in order to take the theoretical results and the results that we have from the labs and test them out in real world environments, because we know that the simulations can only go that far. New technologies have to be tested under real world constraints. Also, seeing the technology in real world opens up other research avenues. That's why at NSF, we have set up a platform for advanced wireless research program, which I will talk about in a bit. We are also engaging in international partnerships. Every country is keen on pursuing excellence in research. And we realize that our researchers need to be able to partner with brilliant and brightest minds, no matter which part of the world they are from. For example, we have an ongoing partnership with South Korean Institute for Information and Communication Technology Promotion, IITP. We also have a range of investments, including establishing research centers that focus on the use of artificial intelligence wireless communications, as well as to investigate the spectrum-related issues via Spectrum Institute initiative. Each of these centers is about $20 to $25 million investments. I also like to talk about the view of next generation wireless systems that I share with some of my colleagues at NSF. But these views are not the official view of national science. I think that the NextG will probably have a true convergence of various wireless systems. The convergence is about bringing together the wired and wireless worlds. It's about bringing together communications and sensing, bringing together communication and computations at the edge, and bringing together hardware and software in a way that we have not seen before. These are not isolated convergence efforts. All of this is going to happen together. That's going to transform how we pursue wireless research. The problems are going to get much more interesting, much harder to some extent, may require much more complex and well-calibrated test environments because of this unique nature of what we think is going to happen to the convergence of wireless systems. We are also trying to figure out how to use the spectrum better. We've been saying this for a long time, but the Federal Communication Commission, FCC in the United States has taken some interesting steps to show the power of spectrum sharing. We are going to see that kind of models explored more aggressively in the near future. For example, we are going to be dynamically using at least some part of the spectral bands, no matter how they were used before. My hope is that with the right form of spectrum sharing strategy, wireless systems are going to start sharing the spectrum in a very trustworthy fashion. What 5G is getting at used to the network being there always for the users, no matter what happens. Then as wireless users, we start using the network because we expect to be always there for critical use as well. And then we need to make sure that network behaves in a resilient fashion, no matter what happens. We want the network to be as resilient as possible, almost like the roads that take us from point A to the point B. The network has to be reliable. It has to adapt to whatever challenges come its way. It has to be secure. No one should be able to take away that functionality from the users. That's what 5G is going to set the expectation that NextG systems will have to be resilient and secure. NextG also has to deliver ultra-reliable, low latency communication, and this is going to be a major shift. We have not conquered that particular domain yet. Conquering the ultra-low latency domain is going to enable some very interesting applications. NextG is also about creating wider broadband reach so that we are not just covering the users in the cities or suburban areas or on the highways. The users expect NextG coverage anytime, anywhere, any part of the country or the world, on planes, on ships. The users even now expect coverage underwater and while hiking, biking in remote areas. Linking all of this together is the notion that network in next generation systems is going to be extremely intelligent at the level that we have not seen before, most likely using machine learning or AI methods. Let us recap. NextG is about convergence, better sharing of spectrum, creating a resilient system, ultra-low latency, being available at broadband speeds anywhere, and being intelligent. These features of NextG systems need to be supported in research that addresses some conflicting use of electromagnetic spectrum. For example, while opening up the new portion of the spectrum, we need to protect the passive science users, such as radio astronomers. 25 years ago, we were using only 10 megahertz of bandwidth for wireless data communications. Now we are hoping to use nearly 10 gigahertz of bandwidth within the next 5 years. That's going to be 1,000 times change. And we need to build better, more efficient electronics, develop channel models for ultra-wideband channels, new spectrum bands, develop advanced signal processing techniques, interference cancellation algorithms, protocols that support the network convergence and new bands. Switching from hardware-heavy to software-heavy network requires development of software-defined functions and programmability during operations to allow dynamic updates. Finally, novel uses of existing wireless spectrum for sensing and power transfer will require joint optimization with communication functions. I would like to pay special attention to the convergence, which is a great thing that has been talked about for many, many years. I remember 3G roadmaps from cellular networks envisioned some form of converged network. With 4G, we started seeing the convergence between Wi-Fi and LTE. But still, we have to sign into a Wi-Fi to utilize this type of convergence. Roaming has become much easier these days. So the convergence happening in some extent is a little bit slower pace, but than what we desire to have. On the other hand, other end of the spectrum, you have new satellite communication companies like Starlink, which are developing constellations of low orbit satellites. Geostationary satellite companies are deploying high throughput satellites, which can provide tens of gigabits per second bandwidth data to the ground. I think we are going to have a combination of cellular, Wi-Fi, and fabric of cellular satellite coverage, and combination of this going to become our connectivity. The user device need to figure out how best you can connect to each of these services. We are also seeing the advent of metamaterial antennas and very interesting designs in liquid lenses and so on. The ability for different bands that satellites are trying to use, the ability to pack a satellite antenna into the form factor of a typical smartphone. I think within 10 years or so, by the time that we get to the NextG era, by perhaps 2028, we are probably going to have integrated antennas that can all three connections, cellular, Wi-Fi, and satellite in a smartphone-sized device. Second layer of convergence would happen in dense urban connections to support extremely high data with ultra-reliable, low-latency communications. The examples that most people are talking include AR, VR, and streaming to support multi-view video. In the back end, a lot of interesting work is happening. The systems are becoming almost entirely software dependent, running on general purpose clusters, with the notions of Open RAN bringing in the idea of decoupled interfaces. Third piece of convergence that's going to happen on the rural side, outside the cities and suburbs. This is where very interesting integration between cellular, satellite, and other forms of wireless connection can happen, including narrowband IoT. I believe this is where the kind of integration is going to happen because it is essential for the users in rural settings. It's essential for the folks in rural settings to survive because they need to feel as much part of the economy as these city dwellers feel like. Most likely the rural networks are going to be the first ones to try mobile edge computing. So the tractors and the farms that are going to be embedded with sensors, they are going to be generating gigabytes of data every second, and data that you cannot afford to transmit because the backhaul connections are going to be more expensive related to what we see in urban areas. So that kind of convergence is fertile ground for trying some of the interesting ideas. So the level of convergence which is requiring us to focus on ensuring that nothing goes wrong. The other aspect is the spectrum sharing. And at NSF, we have initiated multiple efforts on the spectrum to support fundamental research and enabling technologies, as well as establishing centers to increase collaboration between various stakeholders and support workforce development and education. NextG networks are getting bigger, complex, and multi-domain. Spectrum management alone is a time-consuming and data-intensive, perhaps mundane task. Analytical approaches are great for tractable problems. Future needs prompt problems of increasing complexity and difficulty. I believe that NextG networks will heavily rely on artificial intelligence, machine learning methods, much more heavily. AI and ML can help create a self-aware network, which is a network that can learn on the fly. Such network will always be available no matter which part of the world it can automatically, such networks can automatically configure itself. But the next generation networks not only have to be intelligent, they also have to be designed from scratch with resiliency in mind. In fact, the current design approaches rarely pay attention to resiliency unless something starts going wrong. For example, device and networks under some kind of attack or subject to intentional jamming, then we may start asking what type of failure to address, and we would respond to that particular problem. So we are being reactive as opposed to being proactive. That is what that's why we like to design systems from scratch with the resiliency in mind. This is one of the reasons why we at NSF launched the Resilient Intelligent Next Generation Systems Program, or the RINGS program, because we want the security and resiliency to be one of the main drivers of design considerations from the clean state. The program includes many industrial partners, and 2 US federal agencies will be funding research on resiliency motivated ideas. We cannot afford to have disruptions anymore in next generation. It's going to be somebody's car or tractor that can run all over and cause accidents if the network is, for example, is not fast enough. So it is a real-time need for the network to some extent to make sure the network is autonomous and resilient. So that's a very important feature for next generation wireless system. Let me also switch to the concept of ultra-reliable low latency communication. And this is a very important feature of NextG. And we need to focus on it a little bit in this talk. A lot of communication so far has been human to human. Humans are pretty good at dealing with latency. We can kind of find a way to work around latency. We can adapt fairly well. This communication latency that I'm talking about beyond the speed of light constraint. I believe we need to get the network latency below 20 milliseconds to enable many interesting applications like telesurgery, or full virtual reality. It is then possible to see some killer applications that can tap into ultra-reliable, low latency communication. It is not just a telesurgery. It is also human to machine. Can a machine, and then the question is, can a machine react to human expectations over reaction time? And networks has to be ready to this type of uses. And I like to also switch to some of the topics that we fund and look at NSF. We are looking at a range of topics from near term to long term. This list is just an example of research topics that would enable next generation wireless systems. Of course, this list is not limited to the ones that you see here. There are architecture level challenges, there are hardware level challenges, there are software challenges, also challenges of putting all of these ideas together. Of course, all of this work needs to be backed by testing. Testing in a lab may not be sufficient. We need to see many things work in a situation close to the real life as much as possible. This is a 100 million program, the so-called the POWER program, that we have put together with at NSF with a consortium of 30 plus companies. We have 3 platforms that are ready to use today, and you can use these test beds. They are available to anyone, no matter which part of the world you are from. You can use these if you're an academic person freely. We invite you to go and look at them and start using them. We also announced earlier this year rural broadband platform, the ARA platform in Iowa. And this platform is going to be looking at an area of diverse backhaul options, enabling true rural broadband. One can experiment with interesting applications such as smart agriculture and try out other use cases. And all of these backed by nationwide mid-scale infrastructure called Fabric and software emulator called Colosseum, which we are running at Northeastern University in Boston. So we have all these test beds, again, open for any academic use. And anyone can use it freely from academic communities all around the world. As I'm going to wrap up with some additional thoughts, we are not really getting hung up on the 5G roadmap. We advise the research community to be open-minded about NextG, since we believe that NextG is going to be radically different. If you recall how 2G was different from 1G, how 4G was different from 3G, yet it's going to be faster, denser, bigger, but it's going to be convergent, as I mentioned earlier. It's going to be fairly unique in terms of applications that would enable. Do you remember how 5G started about 10 years ago? Researchers are working on many ideas today. Research community may not need to pay attention to the standards or product roadmaps. But we would advise the wireless research community to think broader, think really big and unconventional. We invite the South Korean research community to reach out to the US community of researchers to form research collaborations. We have a joint program with South Korean Institute for Information and Communication Technology Promotion. In partnership with IITP, we are about to choose first awardees under this partnership. The program will continue next year as well. So we at NSF, we like to thank you for listening to this talk. We welcome you to reach out to NSF team or to find partners in the US research community to work on NextG topics. Thanks a lot for the opportunity to speak at this very timely event. And I wish you a very nice day. Please feel free to reach me at mtorlak@nsf.gov for any follow-up questions and any comments. Thank you. Have a nice day.
Thank you, Professor Murat Torlak, for your nice speech. Through this talk, we found that NSF is supporting not only for pure research, but also for some kind of platform, experimental, and some kind of proof of concept. So I found that the role of NSF for next generation wireless is somewhat expanding.